Thanks so much. Thanks for the invitation to come here. It's been super interesting so far, and I'm looking forward to the whole week. I'm going to tell you about some results about Axion-photon couplings in the string Axiverse, and then I'll tell you a little bit about universality in this Axiverse, and I'll explain what I mean by that. But the real message that I want to convey is that we should be using Axion experiments in order to understand better where we live in the string theory landscape, that if we detect an axion, we should understand what we learn about string theory from that detection. All right, so yeah, this will be based on this work with Dottie Marsh, Liam McAllister, and Jakob Moritz. And then at the end, I'll comment on some very preliminary work in progress with a graduate student at Harvard, Junyi Cheng. All right, so just to summarize where we're going, what do? We analyze Axion-photon couplings in the Axiverses that we get from type 2b compactifications on Calabi-Yaos and compare those to known observational bounds. And the punchline is that Axion-photon couplings are more suppressed than one might think. And so what we find is that in this corner of the string theory landscape, even if a few axions can be detected, we're not going to detect the entire Axiverse that one might expect. All right, so outline of where we're going. First, I'll explain how we set up the Axiverse in these compactifications. I'll explain how we compute Axion-photon couplings in the string Axiverse and what we find. And finally, I'll comment briefly on this thing I'll call universality of the Axiverse. All right, so first of all, why care about axions at all at a string theory conference? Well, first of all, there's active ongoing experiments searching for axions, and we may actually detect axions in our lifetimes. So this is like one of the most promising avenues for new physics. And one of the cool things about axions is that their potentials are generated non-perturbatively in general, and they're sensitive to UV physics, but these potentials are computable in string theory. So in order to understand axion phenomena, one really needs to have a UV complete theory in hand. And finally, axions are ubiquitous in string theory. So you get axions all the time from compactifications of string theory. And as I hope to convince you, one can make fairly model-independent statements about axions in string theory. And so as I said at the beginning, axion experiments can teach us about where we live in the string theory landscape. All right, so let's start by constructing the type 2b Axiverse, and what do I mean? So the setup is that we're going to choose some Calabi-Yau threefold. I'll call it X. It doesn't really matter where it comes from, but to be concrete, this is going to be a Calabi-Yau threefold that's constructed via a triangulation of a polytope in the Kreuzer-Skarka database. That doesn't matter so much for the purposes of this talk, but I want to be explicit about where these are coming from. And we'll compactify type 2b string theory on X. We're not going to be fully engineering a standard model in this setting. Instead, what we'll do is try to come up with some toy model of particle physics that will be enough to make some concrete statements. And so in particular, we'll choose some Four cycle in the Calabi-Yau to host a toy model of QCD on a stack of D7 branes. And the important thing is that we're going to arrange that Four cycle has the right volume to reproduce the known gauge coupling of QCD at low energies. So this is going to be important for us. And similarly, we'll choose a Four cycle sigma QED that intersects QCD to be our toy model of QED in this setting. So yes?
Do you have to worry about the backranking of these memories?
The only thing that's going to be important for us, I think the answer is no. I think the only thing that's going to be important for us is the volume of the cycle that those D7 branes wrap. All right, so where do the axions come from? So again, we're compactifying type 2b on a Calabi-Yau, and the effective theory contains some number n of axions, which are given by integrals of the C4 Ramon 4 form over 4 cycles in the Calabi-Yau. So you get one axion for each independent 4-cycle that you have in the Calabi-Yau. That turns out to be H11, but I'll call it N for the rest of the talk. So the QCD axion in this setting, theta QCD, is just the one associated to integrating C4 over that 4-cycle sigma QCD that I introduced in the previous slide. And likewise, there will be a QED axion, which is the one associated to C4 integrated over the QED cycle. And note that these could be the same cycles in the case that we're imagining a gun. All right, so what are our axion characters in this game? We have theta QCD, theta QED, and then a whole bunch of other axions could be around too. And we want to understand the physics of all these axions. And something that you should be worried about, or maybe hopeful about, depending on your philosophy, is that N can be huge. So in the set of known Calabi-Yau threefolds, the overwhelming majority of these manifolds have incredibly large N, right? The largest one in this data set that I was talking about has N equals to 491. And so maybe you're worried that theories with such a large number of axions are already ruled out by observations. After all, each of these axions can in principle couple to photons, and maybe you're worried that a theory with 500 axions, each coupled to photons, is already ruled out. So that's what we're going to try to understand. Yeah?
Do you also consider C0? C0 is the conventional axion.
That's certainly one of the axions that you have. Right now I'm going to be thinking about the phenomenology of the C4 axions alone. There's a slightly different story for the C0 axions. You can also ask about two-form axions, and that's important to do as well, but that's not going to be the focus of what I talk about here. Yeah, other questions before I go on?
Sorry, I always stress this, but it's not that the potential is generally generated only non-perturbatively, instead couplings and fluxes, them perturbatively.
Right, yeah, this is what we were discussing a couple weeks ago. Yeah, so here the potentials will all be generated only by Euclidean branes wrapping 4 cycles. And then of course one can think about what happens if their masses get lifted by other effects. All right. Okay, so a brief comment on how we're going to be choosing the moduli in these settings, because it's important for the story. So I want to stress that the overall philosophy here is that we want to remain as agnostic as possible about moduli stabilization. So instead of having some, stabilization scheme in mind, like KKLT or the large volume scenario or something, we want to understand what happens at every point in moduli space, assuming that the moduli could get stabilized there somehow. And then we can ask questions like what happens if you put in the constraint of having some moduli stabilization scenario that restricts you to some corner in this moduli space. But at this level, we want to understand what happens sort of generically across moduli space. So our moduli space here is a cone. It's not necessarily a 2D cone like I've drawn, but this is just a cartoon. And there's some locus in this moduli space where, as I was stressing before, the volume of the QCD 4 cycle gives the right alpha strong at low energies. And so in particular, what this means is that there's some locus in this moduli space where 1 over alpha strong at some UV cutoff scale is equal to the volume of the QCD 4 cycle. So this is a constraint that we want to impose, and it cuts out some codimension 1 surface in our moduli space. And ideally, what we'd like to do is just uniformly sample along this locus and understand what the axion physics is at each point.
Can I follow up on Shi's question about the descending brain migration? Like, you're computing homomorphic volume, so the coupling that you're taking is a homomorphic coupling, right? But then in experiments, you're going to observe physical coupling. And then in the presence of the descending brains and somewhat large G string, there could be a sizable threshold correction that changes the relation between the homomorphic coupling and physical coupling in a very sizable manner. How do you estimate that?
Right, so what's going to control the gauge coupling at low energies is the beta function of QCD. So you do have to do that matching between high and low scales.
But in supergravity, not only do you have beta function, but you also have a threshold correction that comes from integrating out tower states, and that could be really sizable. And then I don't know how to estimate that when G-string is not symmetric.
Okay, I'm not exactly sure what you have in mind, but maybe we can discuss afterwards. It's a good question. All right, so so what we'd like to do is sample along this locus, but what we found, experimentally, so to speak, is that for a given geometry, the observables that we're interested in depend pretty weakly on the location along this locus. And so instead of trying to sample all along this locus, instead we're going to restrict ourselves to a particular point in this moduli space along this locus, which the name of this doesn't matter so much, but we call it the tip of the stretch Kähler cone. And this is where all the curve volumes in the Calabi-Yau are at least 1. And this is a crucial point for the sort of behavior that we're going to see later on in the talk, is that we're imposing that all of the force cycles and all of the curves have volume at least 1. And that's the so-called geometric regime. All right, so that was just about how do we pick moduli in this context. And I want to stress that now we have the capability through this awesome software that my friends developed to construct these semi-realistic Axiverses from compactifications on these Calabi-Yaus. And the first thing we should ask is whether these models are ruled out by observations. So as a first study, we had looked at QCD theta angles in this Axiverse and found that the strong CP problem is almost always solved when the number of axions is bigger than about 20. But what I want to talk about in this talk is some results on studying Axion-photon couplings in this Axiverse. And the reason I want to focus on this is that some of our best constraints on axion physics come from experiments that are probing Axion-photon couplings. All right, so what I want to ask is, given an axion theory that comes from one of these Calabi-Yau compactifications, how do we read off the axion-photon coupling GA gamma gamma? So the Lagrangian that I have in mind is written in terms of Calabi-Yau data. So I have some kinetic term for my axions. I have some coupling of my axions to photons via the F wedge F coupling. And finally, I have some potential for my axions. And this Lagrangian is completely characterized in terms of Calabi-Yau data. So everything here is a result of the geometry. In particular, this KAB is the Kähler metric. These instanton scales appearing in front of the potential scale like e to the minus 2 pi times the volumes of the 4 cycles. And these charges are the instanton charges, which are determined by charges of effective 4 cycles in the Calabi-Yau. So everything here is written in terms of the geometry. And what we're going to do is to compute these geometrical quantities for a large ensemble of Calabi-Yaus and ask what sort of axion-photon couplings come out. And so we want to know, given a Lagrangian like this, how do we read off GA gamma gamma? The prescription is incredibly simple. All we do is canonically normalize the kinetic term and go to a mass eigenbasis so that we end up with a Lagrangian that looks like this, where our kinetic term is canonically normalized and we have some mass eigenstates. And then we can read off the axion-photon coupling that a given experiment is sensitive to just by adding in quadrature the coefficients that appear in front of the F wedge F term. Yeah?
Usually the axion can also be gauged with photon by mixing this QCD.
You mean like the E over N coupling?
That's right.
Yeah.
Well, actually I was asking more about the modeling dependent correction. So axion can couple to QCD and QCD coupled to pion and then pion to gamma. Is that included in your formula? It seems that the formula you have is purely a medium.
Yeah, maybe I'm not understanding your question exactly, but it is true that I've left something out here, which is that there's also a lambda QCD to the fourth terms. And so we also have a QCD axion that couples to photons. And that coupling is just the usual coupling that you would get for the QCD axion.
I thought that also contributes to the decay rate of the axion.
It definitely will. And that coupling will show up here as one of these coefficients. Yeah. Yeah. Other questions? All right. Okay, so the question is, in a basis where all of the axions are mass and kinetic eigenstates, what are the couplings of these axions to F wedge F? And there's two crucial facts that are going to describe what we see. The first is that in the geometric regime, remember where all the cycles are big enough, these instanton scales are exponentially hierarchical. And the second fact, which is something that you wouldn't expect from a bottom-up perspective, is that there's always an E&M instanton. So there's always going to be one of these instantons that contributes with the same charge as the axion coupling to F wedge F. And these two facts, I'll explain this in detail in a second, but these two facts lead to this general lesson that only axions heavier than the QED axion couple to photons. And that's sort of the main point. All right, so to explain how this works, let's look at a two axion example. So let's consider a theory with two axions where my potential has two terms. I have a lambda heavy to the fourth term coming with some charge Q heavy, and I have a lambda light to the fourth term coming with some charge Q light. And finally, I have my coupling of the axion to F wedge F, which comes with some charge QEM. And importantly, I'm going to take lambda heavy to the fourth to be much, much bigger than lambda light to the fourth. So this is sort of like a typical, simplified model of what we would see. And as a first case, let's look at what happens when this E&M charge of the E&M axion is equal to Q light, okay? So what we'll do is integrate out the heaviest direction, which in this case is Q heavy dot phi, to obtain a one-dimensional effective theory for the lighter axion. How do we do this? We decompose the field space into a heavy direction and a light direction. So I just take my axion field space and I decompose it into something that depends on phi heavy and some perpendicular component as well. And if I take this decomposition and plug it in to my F wedge F term, what I see is I take my F wedge F term, which couples to Q light dot phi, and I plug this decomposition in. What I see is that nothing special happens. Both phi heavy and phi light couple to photons. But now let's do the second case. So we have our same theory with two axions. And now we'll consider the case where this Q E&M is equal to Q heavy. So let's repeat the exercise. We integrate out this heaviest direction to obtain a one-dimensional axion theory. And now when we do this, we can again plug in this decomposition into our F wedge F term. And we find that Q heavy dot phi, if we plug in this decomposition, takes this form. And by assumption, this second term is 0, right? Because Q heavy is perpendicular to Q perpendicular. And so what we find is that with this choice of Q, E, and M, only phi heavy couples to photons. And this is sort of a toy version, oops. Okay. This is sort of a toy version of the general picture that we see, that only axions that are heavier than the mass scale set by the QED axion couples to photons. So what does a typical model look like if we look in our ensemble of Calabi-Yau compactifications? Here I'm showing you the axion-photon couplings that we get from a compactification where n is 200. And on the x-axis, I have the coupling of individual axions to photons. And what we see is that maybe 3 of the axions have sort of non-trivial coupling to photons, but most of the axions in this compactification have totally negligible couplings to photons. In other words, they're invisible. And so the lesson is that in this landscape, even if we detect an axion or a couple of axions, we're not going to detect this whole Axiverse. Yeah.
I thought some of the many creative experimental ideas involve the QCD couplings, not the.
Yeah, sorry. I've gotten in trouble for calling this invisible before, and I think that's what you're saying. So by invisible here, I just mean, I'm just talking about its coupling to photons. I'm not saying that it's impossible to see these axions through any other experiment. I think that's something that we should focus on. I'm just saying that with axion-photon coupling experiments, we're not going to see these ones because their axion-photon couplings are too small. All right, so this is a general mechanism, and here on this last slide, I was talking about individual couplings of axions to photons, but experiments are not sensitive to these individual couplings. They're sensitive to total effective couplings of axions to photons. So I've said that only axions heavier than the QED axion couple to photons. And what are the consequences of this fact for detection prospects? Well, suppose that in this mass eigenbasis, the distribution of decay constants is something. I don't know. I just made a Gaussian in Mathematica. This isn't a real distribution. If the axion-photon coupling that experiments are sensitive to gets contributions from every single one of these axions, then this sum is dominated by the very smallest f's in this tail, and you get a large axion-photon coupling. But if, like what I'm telling you, you're supposed to just choose a sample of a few of these axions from this distribution, then this sum that gives you the effective axion-photon coupling is generically suppressed because you're not picking up the most extreme values in this distribution. Okay, so let's talk about axion detection. How do these experiments actually go about looking for axions? So they're sensitive to this coupling we've been talking about, GA gamma gamma theta F wedge F. And the fundamental of this experiment is that we can hope to detect axions via conversion to photons in a large magnetic field. So here's my picture of how I think this works. So you have the sun, which hopefully generates some axions that are streaming towards Earth, and we can place a big magnetic field on Earth and hope that that converts the axions back to photons, and we can see some excess in our signal. All right, so that's how the experiments work, and there's a couple experiments that I want to focus on. The most current, best, broad mass range experiment right now is this experiment CAST, which looks at solar axions. And I'm shading here the region that is already ruled out by CAST. There's a future experiment, EAXO, which is projected to give bounds in this range here. And now I'm going to show you what we actually find when we look in a large ensemble of Calabi-Yau compactifications. So this is what we see. So the important things to note from this plot is, first of all, that GA gamma gamma increases with n. That's maybe surprising, and I'll talk about that in a bit. Another thing to see, which is maybe the most important thing, is that even though GA gamma gamma increases with n, they're still mostly unconstrained by these experiments. So to answer the question that I brought up in the first part of the talk, are the axions in this landscape, are these theories with 500 axions ruled out by current bounds on axion-photon couplings? The answer is no, they're fine. Though we do start to push up against future bounds at large H11, which is exciting because maybe we'll detect something. Okay, and I want to stress that even in these models that start to be constrained by future experiments at large n, only a few axions will be detectable, so it's not the whole 500 set. All right, so that concludes this, the first part, which is about axion-photon couplings. Before I move on, any questions? Yeah? Those are the three that are heavier than the QED axion. Yeah.
If the heaviest ones, the couple of ones don't make the
Exactly. Yeah. I lied a little bit when I said that the light ones don't couple at all. They do couple, but in a very suppressed way that depends on the ratios of mass scales between those. Okay. All right. So now I want to change course a little bit and talk about this concept of universality in the Axiverse. And this is just a fun little aside about random matrices. I want to stress before I talk about this that this is extremely preliminary work. And I won't have a lot to say about what it could mean. I just want to present something to you as a curious coincidence. Okay, so what do we see in all these studies of axions in Calabi-Yau compactifications? We've done many, many scans at this point, over hundreds of thousands of Calabi-Yaus, and we find that a similar pattern emerges no matter what observable we want to talk about. So what we find is that as n increases, first of all, axion decay constants increase.
You said increase, but it says decrease.
Sorry.
So which one is it?
Decrease. Thank you. Yes, axion decay constants decrease. Axion-photon couplings, which go like the inverse of the decay constant, increase. Dark matter relic densities of axions decrease. The number of axion minima stays order 1, even when the number of axions becomes huge. As I mentioned, stringy contributions to the QCD theta angle decrease. And all of these behaviors are a consequence of one underlying fact, which is that as n increases, hierarchies in instanton scales increase. Okay, so as we go up in n, what we're seeing is that scales in these lambda I to the fourths increase a lot, the ratios of them. And so a question that I'm interested in is how do we capture this behavior with a simple model? Because these are all, we ran a separate scan for each one of these. Well, not separate, but we had to look at hundreds of thousands of Calabi-Yaus to understand each of these points, and they're all pointing to a similar underlying structure. Okay, so what drives this behavior intuitively? Well, there's an isotropic expectation, which is that if all of the 4 cycles in your Calabi-Yau are roughly of the same size, and you do this thing that I mentioned, that you set the scale of these cycles to match the QCD gauge coupling at low energies, then what you find is that decay constants don't decrease as a function of n. Instead, what you find is that for all n, decay constants sit around 10 to the 16 GeV. And this is sort of the classic historical string Axiverse expectation of what would happen. But instead, what we see is that the 4 cycles are not all roughly the same size. Instead, the Calabi-Yau looks more like this, where the cycles are all hierarchically separated. And it turns out that this hierarchy in 4-cycle volumes implies hierarchical axion physics. And the question is, can we model these hierarchies? So that's what I'd like to do from a practical standpoint, is to be able to model these hierarchies in such a way that we can reproduce some of the features that we've been seeing in these studies of the string Axiverse. Okay, so I want to stress again that this is preliminary. It's just a suggestion at this point, but I want to point out a kind of curious coincidence. Okay, so we know how this goes. We can consider a set of random n by n Hermitian matrices where the entries are drawn independently and randomly. And the set of their eigenvalues, as we know, converges to the famous Wigner semicircle. So, for small-ish matrices, you get these large fluctuations in the eigenvalue spectrum, but as you increase n, they converge to this Wigner semicircle. We can also talk about the level spacings of this ensemble. So I'm defining the level spacings as the difference between adjacent ordered eigenvalues divided by the average of these eigenvalue differences. Okay, so that's the level spacings. And these level spacings also converge to some distribution, which is called the Wigner surmise. So again, at small n, we get these large fluctuations, but at large n, they converge to this analytic expression, which is the Wigner surmise. Okay, so I want to see if we can use something about these random matrices to represent what we're seeing in the Axiverse. And so what I'm going to do is pick a single Calabi-Yau with the largest H11 I know, which is 491 in this database. And I'm going to compute the following quantity, which is the logs of the 4 cycle volumes divided by the average of the logs of the 4 cycle volumes. And I'll order these quantities di so that they go from smallest to biggest. And I can plot these. This gives me an idea of the spectrum of 4 cycle volumes in the Calabi-Yau. So on the x-axis is just the label, the index that labels the ordering of these 4 cycle volumes. And on the y-axis is this quantity d sub I. And I can also choose a single random matrix that has size 491 by 491 and compute this quantity, the level spacings that I showed you before, and also order them so that they go from smallest to biggest. And I can plot these on the same plot, and I get something like this. So this is just a suggestion that maybe there's some underlying structure that is driving these sorts of patterns that we see in the Axiverse that's pushing hierarchies to be large and driving all this Axion phenomena that we see. All right, so to conclude, what have we talked about? I hope I've stressed to you that Axion experiments are a really exciting place to look for new physics. We may actually detect them in our lifetimes, it's possible, and before that happens, we should really understand what string theory has to say about axions. And in the context of the type 2b Calabi-Yau landscape, only a few axions couple to photons. Even if we detect one axion, the majority of the Axiverse is invisible to Axion-photon coupling experiments. Then I explained that hierarchies in Calabi-Yau geometries lead to new expectations for the scales of the problems. And I showed you this weird, curious coincidence between 4 cycle volumes and Gaussian random matrix level spacings. So with that, I will conclude.
Hey, thanks for the nice talk. Can you comment on the role of supersymmetry breaking and what happens with the saxions, depending on what you've done with those?
Yeah, definitely. So in this work, what we did, so this kind of has to do with what I said about moduli stabilization. So we're assuming that the moduli get stabilized perturbatively, and so there will be a mass hierarchy between the saxions and the axions in what we're thinking about. So the saxions really play no role in what I'm describing here. We're assuming that they get stabilized at some high enough scale. The role of supersymmetry breaking is encoded basically in the prefactors. It's encoded here in the lambda I to the 4th. So there's a factor in the instanton scales from the perspective of the 4D potential that depends on the scale of supersymmetry breaking. The results depend somewhat on what you set that scale of supersymmetry breaking. We did the most naive thing and just took it to be to go like 1 over the volume of the Calabi-Yau. But yeah, in general, one should think carefully about how to do that. In the work that I mentioned before, where we calculated stringy corrections to the QCD theta angle, we were careful to tune the scale of supersymmetry breaking to be as low as possible to give as big a contribution as possible to the QCD theta angle.
Question on Zoom, and then we'll come back to the room.
What can you tell us about the masses of your axions?
Yeah, so they, the historical picture is that the masses are log flat. They're not quite log flat here, but they don't have an extremely strong dependence on the number of axions in the same way that the decay constants do.
But log flat in what scale of masses or whatever? Can you meaningfully answer?
Oh yeah, I mean they can have masses all the way down from the Hubble scale up to the KK scale.
Well, of course, that's really important because there are ranges in there where axions could be very interesting astrophysically as dark matter that would produce unusual effects, either at scales of galaxies or even bigger scales.
Mm-hmm.
There also are ranges of axion masses which are dangerous cosmologically because too much dark matter might be produced.
Definitely. That's something we've looked at as well, actually, at the amount of dark matter that you get from the misalignment mechanism. And the nice thing is that the amount of dark matter that you get from misalignment decreases as a function of n. So it is true that for compactifications with small n, you do often get way too much dark matter and overclose the universe. But as n increases, the amount of dark matter goes down. And there's actually a nice tension between the directions that the constraints push you, that as you go up in n, the dark matter relic density decreases, but Axion-photon couplings increase. And so you can try to ask whether that pushes you to any particular place in the landscape.
Well, I'd be curious whether there's a reasonable range where you get a sensible amount of dark matter that you can actually detect.
Yeah, I thought I had a...
Personally, I think that there's at least as good a chance of detecting axions that way as by Axion-photon couplings.
Right. I thought I had a slide about it, but I don't. Yeah, I think it's around like n of 50 or 100 or something, where you get a bunch of axions that are in the right range, but I don't remember the exact numbers. And also, it can vary widely from Calabi-Yau to Calabi-Yau.
Actually, one last question. You see, if you have a few in the right range, I wonder if you avoid having some. Sorry, when you say in the right range, you mean that there aren't heavier ones that overproduce dark matter?
Exactly. Yeah. So see, it's definitely possible to have Calabi-Yaus with the right n, such that all of the axions produce the right amount of dark matter and no more.
Okay. Thanks.
You said something about drawing model
say,
independent. Oh, I'm sorry.
I apologize. I want to say one more thing. You shouldn't be satisfied, consider it finished when you decide you have the right amount of dark matter. It's really important what the axion masses are, because there's a few orders of magnitude of axion masses where they're interesting astrophysically because they could be distinguished from ordinary cold dark matter. Above or below that range, they can't be distinguished from either ordinary cold dark matter or or a cosmological constant.
Do you have in mind like fuzzy dark matter from Axion?
Well, fuzzy dark matter and downward from there from a few orders of magnitude down to what's called the sigma 8 anomaly could possibly be interpreted as a sign of an axion.
Mm-hmm. Mm-hmm.
So roughly from 10 to the minus 22 to 10 to the minus 25 EV is a good range where you might actually get astrophysical evidence for an axion.
Yeah, and we definitely have axions in that range a lot.
So I understood you were looking for model-independent conclusions that you could draw about axion physics. Suppose that the Calabi-Yau is not in the Kreutzer-Garkert database. There are probably lots of Calabi-Yaus that don't have that property. Or suppose, even more radically, that it's UV complete, but not because of string theory. Can you say anything?
Yeah, not really at this point. And that's honestly, that question is the motivation for the last part of my talk. I want to understand like which features are the essential features that drive this behavior. And then the next step is to understand whether those features are present in any of the scenarios you just described. Also beyond that, I mean, even, some things I think about are like, what if you're not compactifying on a Calabi-Yau? What if you're compactifying on some more general manifold? What if you're not compactifying on a manifold at all and you have some non-geometric compactification? These are all things that I think we should understand soon. But I'm just taking baby steps here. Yeah.
Do you have any understanding about F theory? Because in F theory, we have so many Calabi-Yau compactifications with huge Hodge numbers. And if I understand correctly from your talk, is that if the Hodge number is somewhat large, then it's already ruled out by experiments or observations.
Well, that's a question, I would say. Like the trend is that as n increases, the constraints from Axion-photon coupling experiments gets stronger, but I haven't said exactly at what n you become completely ruled out, and I think that's a really interesting question to answer in F theory.
Yeah, I remember vaguely that like some of these axion hunt experiments rely on just trying to catch the resonance with the single axion, and if you have a bazillion axions with slightly different masses, does that cause a problem for these?
No, because the experiments that rely on like resonating some cavity, they are very sensitive to how much of the dark matter axions make up. So those resonance-based experiments are usually in some fixed region of masses for axions, and assuming that you have this like bath of axions around us that makes up, an order 1 fraction of the dark matter. And so having a ton of axions spanning a huge range of masses is not a problem for those experiments.
Or it's basically only one axion will actually contribute.
Exactly.
Okay.
Any further questions? Okay. If not, let's thank the speaker again.